this lecture, we want to summarize what we have learned in the previous class. So, we want to give an overview of various fixed frequency current mode control architecture. So, we will give an overview of fixed frequency current mode control architecture, we will summarize various mixed signal control, current mode control as well as fully digital current mode control. So, if we go for digital current mode control, because it is a 2 loop control where we are considering, that means if you take analog, I will say analog current mode control, where we have this Vref, then there will be V0, there will be a controller, then controller will go to a comparator, and this is my inductor current. So, then it will go to a RS latch. So, I am talking about peak current mode control. So, this is my switching clock, and then it goes to my DC-DC converter. So, this comparator, as long as the inductor current is, if inductor current crosses this, so it will be plus, it will be minus, and we are taking the inductor current sense from here, and then we are taking the output voltage here. So, this is my output voltage, this is my inductor. So, it is a 2 loop control, we have an inner current loop and the outer voltage loop. Now, in this control, when you go for digital control, we are taking all the time the digital loop, voltage loop in digital. So, that is voltage loop in digital. Now, the architecture will differ based on whether the current loop is in analog or digital. So, first is the current loop in analog, where you can have a peak current mode control, valley current mode control, and we have also discussed that we can also have average current mode control, architecture. In the digital, so this is a mixed signal implementation where the current loop in analog, and we can retain the fast dynamics of the current loop. Now, if you go to fully digital, then your current loop in digital domain, where you can also have peak current mode control that we have discussed, valley current mode control, and we can also have average current mode control here, but we have not demonstrated in this course because these are somewhat advanced topic. So, one can, if some understanding of digital control is developed, then one can try to search the literature, the research papers, or maybe some commercial product. So, this is called fully digital current mode control, where both current and voltage loop are digital domain, and for the mixed signal, voltage loop already in digital, so current loop in analog. And we already know about the architecture. This is like your analog comparator, and this is a sense current in the analog domain, and your voltage in the digital domain. So, we know about all this architecture, and we know about the control waveform. That means, here we are talking about the peak current mode control and interval 2 sampling that we have discussed in the previous lecture, and valley current mode control also in mixed signal implementation. We have discussed that if you just turn off the switch at the rising edge of the switching clock, and then switch will turn off on when the inductor current will touch the valley current, and by that process it will continue, and it is under leading edge modulation with interval 1 sampling. And we know, we have also discussed that if you remove this RS latch and represent using a the configurable algorithm, digital algorithm, then the same hardware can be used for peak as well as valley current mode control, because if you want to go for wide duty ratio operation, maybe one can go from peak to valley, but for that purpose we need to sense the full current. But in many implementation, actually the current is sensed, like only high side current is sensed. So, in such cases we can go for only peak current mode control in mixed signal realization. For valley current mode control, we need to sense the low side current. Okay, and when you go for variable frequency architecture, because valley current mode control, if you go for low duty ratio operation, then it is inherently unstable, for then you need to add you need to consider ramp compensation. Now, when you go for constant on time control, which is a very popular solution, then you will get an inherently stable current loop, but it is also easy to sense low side current, because you can sense through the RDS on of the switch, because it is a ground referred, okay, or you can put a small resistance in series with the, you can put a small resistance here as a sense resistance, and it is a ground referred, so you can directly sense. But for peak current mode control implementation, you need to actually sense the high side current in mixed signal. But if it goes to fully digital current mode control, even with sensing the low side current, because you are taking the sample, the valley current, and you emulate the rising slope in the digital domain. So, you can sense the valley current and still can implement peak current mode control if you go for fully digital current mode control architecture. So, in fully digital current mode control architecture, if you go for peak current mode, you see we are sensing the valley current before the switch turns off. That means you can just take the, you can sense the low side current, which is very easy to sense, and you can emulate in the digital domain. Another problem can be addressed because there is a 1 cycle delay, because in peak current mode control, if you see, if you want to implement the peak current mode control for a very low duty operation, some major difficulties are there. So, suppose I want to do for analog control, for example. So, in analog control, the duty is very low, okay, and suppose you have some spike in the sensor. So, first of all, the current sensor can have some spike, and you have a very low time because for high frequency. So, you need to blank some time here in analog implementation, and this time is so low, for the comparator point of view, it will be very tough to take decision. That is why for low duty operation in analog control, people go for constant on time control, because if you go for valley current mode control, which you have a longer duration of off time, but it is inherently unstable for low duty issue, and that we have discussed in our previous NPTEL course, that is our control and tuning method in switch mode power converter. But in digital control, since we are actually taking the valley current here, and that is processed for the whole cycle, you get a full time, and you are actually comparing in the next cycle using internal to the digital. So, these are digital comparator. In fact, digital comparator means it can be a simple subtractor, and you can check the difference by looking at the MSB. So, you do not need a physical comparator, it is just a 2s complement subtractor, and that can be very fast, and there is no switching noise, because you are taking the sample at the because I am just talking about this valley current mode control. Even though there is a noise, so I am capturing the sample here, I can sample here before switch turns on. So, I am getting a clean sample, and then I can add RAM, right. So, we can avoid such switching noise, and since the inside the controller it is noise insensitive, and our digital sawtooth already is very fast because it is a sawtooth, and you are making the, because we have discussed various architecture of RAM, this emulation RAM, right. So, we have discussed RAM, and the comparator means just a subtractor. So, you can make this operation extremely fast, and you can actually realize peak current mode control even for low duty ratio operation. So, that means when you go to digital control, many possibilities which are difficult in analog can be easily realized in digital. In fully digital, if you take one sample delay for the voltage loop also, you are taking one sample delay. So, current is already one sample delay, otherwise you cannot make it feasible, and voltage also you can delay by one sample, and we can also take voltage a little bit earlier. So, there are many things, but we need to be very careful about the stability analysis, because in this course it will be very tough to consider all the case studies in the stability, but we will show a few ideal or maybe one or two realistic case study, and it will actually enable the participant in future to actually go for use the methodology that we will discuss to analyze stability for various possible delay options, how to analyze stability. But one bottom line is this: you can implement various digital control architecture, peak, valley, etc. In this fully digital current mode control. Similarly, if you want to compare, the first thing in fully digital, that means mixed signal. So, if you sense, let us say you are only sensing low side current, low side, I will say low side current sense. So, this is easy for a buck converter because low side switch is very easy to sense. Then In fully digital, you can do peak current mode control, but here it will be valley current mode control because current loop in analog. Okay, and low side current means because it has to compare with the physical current, right? So it will be valley current mode control, and you can implement peak current mode control. And if you go for variable frequency architecture, even you can implement peak valley in the same architecture itself, but we are not going to discuss here. In fully digital, you can implement peak current mode control. Now I may ask, can you also do valley current mode control in fully digital? Why not? You can also sense, that means if you take the low side current, that means I am talking about the low side current. This is the inductor current, low side current. Now if you can sense, maybe after reasonable this time, maybe if you have to provide some delay because you have to avoid this switching point. Now you take the sample somewhat closer, after that is settled down, maybe give some delay, then this you process for the next cycle and implement a valley current mode control. So it is still possible that using low side sensing, you can go for both peak as well as valley current mode control, but there will be some delay, so that you have to take into account. So that means fully digital current mode control is flexible, and you can also muxing using a single ADC. These two ADC can be muxed here because they are taking only one sample per cycle, but the fully digital control, actually this is a quantized current. So that means you will have a limit in terms of quantization, which has a similar problem in voltage mode control. So you have a quantizer here, you may have a quantizer because of this Repul emulator, and you also have a quantizer of ADC. So it is very important to match this quantization, otherwise you will end up with lot of instability in this architecture. Whereas here you have only analog current. So the quantization is primarily defined by ADC and your Q factor of this compensator, and we will discuss in fixed point implementation. So here we have shown the peak current mode control architecture of fully digital and current mixed signal. Here we need a valley current sensing for peak current mode control implementation. Here we need peak current sensing, or basically high side current sensing for peak current mode implementation. So these are the difference. So you can think of many possible architecture. So I am just giving you some basic idea. So I hope you can take it forward. So in summary, we have discussed various fixed frequency current mode control architecture. We have summarized mixed signal current mode control and possibility of various valley and peak architecture. We have also discussed some fully digital current mode control architecture, and we have shown that even using sensing either side current, you can implement both peak as well as valley current mode control. And we need to also simulate and model this. So we will implement at least fully digital and peak current mixed signal current mode control using MATLAB simulation, so that we will realize how to implement this control logic, and then you can think of more advanced control algorithm for your further study. So with this I want to summarize here. Thank you very much.